Good afternoon to all of you. I think who are attending these particular courses or ready to listen this the live interaction of the second live interaction of the Introduction to Solidification Processing course. I think we have already shared these 3 modules, and I think 4 modules is going on. And these 3 modules are thermodynamic principle of the phase transformation. We started with this thing, basic thermodynamic principles to understand the solidification processing. Then solidification theory we have explained in principle of the solidification in this particular module. Then I look into the application side of the solidification processing, that is the started with the solidification casting process. And of course, after that, we're supposed to discuss with this thing solidification of the welding and additive manufacturing processes, application of that. And finally, the various solidification techniques associated with the this particular course, basic course. So if we observe the overall course structure, then we have tried to some basic understanding relevant to the solidification processing and application towards the welding, additive manufacturing and casting processes, and to understand basic theory and where using this theory, what way the different microstructure usually form. That perspective we try to explain in these cases, but I feel that this particular course is more focused on the theoretical aspects, and that's why it is maybe able to understand the who is starting the BTech level, BTech students, or even maybe useful also in MTech student who has not gone through this particular courses. So this nucleation in the pure metals, then what are the growth of the pure metals and growth of the, in case of the alloy system, solidification of the alloy system, and some cases we explain the simulation of the nucleation and growth process. And that is the overall structure or overall aspects or maybe elements associated with the solidification processing course. Now, I observed that there is no such questions arises this associated with this course, and even for the live interaction, no questions raised. But I like to mention a few critical or important things associated with this course. One is that if we look into the pattern of the assignments, if you observe carefully, that we put the questions related to only 2 marks questions. And there's the multiple choice type questions, and of course both theory as well as the numerical problems also there associated with that. So similar pattern what you observe in the assignment problem, the same kind of the following will be following in case of the end semester, that means your exam process, also examination process. The similar way we can, that means you can be prepared with the types of the questions with the assignments is given. Try to understand that what are the questions that means the link with the questions with the theory. Then it will help you to answer the questions in the semester end examination for this particular subject. Now, if you're really interested to look into this particular course, then I already mentioned that there are so many references book associated with that, and there are different reference book. They explain the different topics of the solidification processing. For example, very basic, if you under thermodynamic principle, phase transformation in metals in alloy, then the first reference book is most important. Then even for the fundamental different aspect, other aspects which I have not covered in this particular course, in to say that fundamental of the solidification, also the second book is the most important, useful books associated with that. Now, if you look into the application of solidification process to understand the microstructure formation, then in case of the casting, the reference 3 is more useful. If you understand the heat transfer associated with the casting process also, then reference 4 is the useful book. And if you look into the metallurgical aspect associated with solidification process and which is aligned to the welding, then 5th is the most suitable book. And overall understanding of the physical metallurgy, then we can follow the book 6. So all the 6 different textbooks mentioned here, they cover up the different topic or different aspects of the solidification processing. And then I believe that if you follow all these class notes, to some extent, your understanding to go into depth associated with this different reference book, that will be more useful to complete understanding of this or grasp of this particular course, the solidification processing. Now, few critical part I'm just trying to explain once again. This associated with this course. One is the solidification in casting process. What are the simplest way we understand the solidification casting way? Because I'm not explaining the theory part. Theory you already know. But in casting process, when you try to explain this in case of the alloy system, then we can that in the alloy system there is a range of temperature over which the solidification occurs. That is the, and ideally it can be between the solidus and liquidus temperature. And what is happening in the solidus and liquidus temperature? In the alloy system, most of the understanding associated with the solidification process to apply in the casting on the or welding processes. So in case of the casting, we're assuming no solid diffusion and complete diffusion in liquid. This is one particular case when you try to the solidification occurs starting with the liquidus temperature gradually moving to the solidus temperature over a range. And if you look in the binary phase diagram of this alloy system, then if you see the liquidus line and solidus line, the slope are different in this case. So in this case, gradually liquid phase to transforming to the solid phase. The in between is a mixture of the solid and liquid phase. Now, ideally in equilibrium conditions, the solid phase will try to follow the solidus line, and liquid phase will try to follow the liquidus line. But it is a very ideal situation, and practically the rate of the solidification can be different. So in that case, in practical situation it occurs like that no diffusion usually occurs in the solid phase, and complete diffusion in liquid phase occurs, but with some external aid to make it happens the complete diffusion in the liquid phase. This is one case, and another case we're assuming there is no solid diffusion occurs, but limited liquid diffusion occurs in the liquid phase. So in these two cases, how the structure forms, and based on that we can predict that the profile of the concentration profile is associated in case of the alloy system. Now in alloy system, the solidification modes, during the solidification of the pure metal, we see usually the solid liquid interface is usually planar. Planar interface we move and we try to analyze in a pure metal that it's gradually moving in the solid liquid interface in the planar. Now then perturbation may occur in the planar interface with the depending upon the stability of the solid liquid interface. Can be maintained with specific conditions for the rate of the solidification and the rate of the growth rate as well as the temperature gradient. Both are influencing parameters to decide the stability of the solid liquid interface. So then stability decide what kind of the interface will be stable at what conditions. That is the main aspect of the solidification of the alloy system. Now in case of the pure metal, it's a solid liquid interface is usually planar, but in case of the alloy system, the solidification in the solid liquid interface can go planar mode or cellular mode or dendritic mode depending upon the solidification conditions and what kind of the material system, basically alloy system, we are considering. Based on that, different mode of the solidification might occur. So here that mode we'll try to explain here. So basic solidification modes, if you see the planar interface, the solid liquid interface moves in the form of plane. Then it creates some kind of cellular structure. Another mode is the solidification mode, is the cellular mode, or is the columnar dendritic mode. If you see the dendritic structure, it's called the one primary dendritic arm is there, and gradually secondary dendritic arm form and tertiary dendritic arm form different way. That is called the columnar dendritic structure. And there's another mode that is called the equiax dendritic mode. So dendritic structure is there, but overall grains shape is more or less the similar size of the grains, but within these grains, the dendritic structure exists. So these are the 4 different types of the modes of the solidification occurs, and it actually decided by the solidification parameters. So what kind of the mode of solidification usually occurs during the solidification of an or pure metal, or in case of the alloy system. See, here I'm just talking about the solidification in casting, and that is called the interface stability we are trying to explain in case of the alloy system. Let how it works. So constitutional supercooling means that during the solidification, due to a compositional solid changes, results in the cooling a liquid below the freezing point ahead of the solid liquid interface. So some compositional solid changes during the solidification process. If you observe that, or if you, I already mentioned that we're starting from the liquidus temperature, and gradually it will try to follow the solidus line, and liquidus it will take as a reference of the first figure. So if it's ideal equilibrium, under equilibrium conditions or ideal situation, then when that liquid phase is gradually converted to the mixture of the solid and liquid phase by reducing the temperature below the liquidus temperature, in that case, if you see that the solid phase will try to follow the solidus line, and liquid phase will try to follow the liquidus line, then there might not be any questions of the compositional changes or the accumulation of the composition or composition gradient ahead of the solid liquid interface. This kind of things will not be there if it is follow the equilibrium solidification condition or in the ideal situation. But if there is it doesn't follow exactly the solidus line or liquidus line during the solidification process, then some might be having some compositional changes or concentration distribution can be different. So this compositional changes occurs ahead of the solidification front, which is termed in the form of during the cooling phase in the form of the constitutional supercooling. So that compositional changes or compositional gradient existence of this thing brings the constitutional supercooling. So therefore, it actually decides the breakdown of the planar interface, solid liquid interface conditions during the solidification process. So let us look into consider the solidification of an alloy C0. Say initial composition of the alloy is the C0, and then at the steady state conditions and with the planar solid liquid interface. So in that case, we see that red zone is basically when it is gradually reducing the temperature. The red zone is basically zone of the constitutional supercooling, because there might be having some compositional differences in the liquid phase. So that actually happens at the zone of the solid liquid interface, between the solid and liquid interface. Now, in compositional, because of this compositional changes, this creates some kind of the constitutional supercooling situation. Now, if you plot it here over the range of the delta T temperature, and of course in between the solidus and liquidus temperature, and if you see look into the second figure, here the actual slope is there, that means in equilibrium conditions, but due to the presence of the constitutional supercooling, so supercooling, the slope at this particular point, if you see, which is different, the slope is different, but this slope is higher than the actual slope. So therefore, actual slope equal to G. But let us, before that, we try to understand what is G and R. These are the two solidification parameters. R is the growth rate and G is the temperature gradient, the ahead of the solid liquid interface. And DL is the diffusion coefficient of the solute in the liquid phase. L square by the dimension equal to L square by T. That means diffusion length, T equal to here time, and L by T. L is the length scale, time scale, and temperature gradient is the temperature by length scale, theta by L. So these are the dimension of the R, G, and diffusion coefficient of the solute in the liquid phase. Now in the slope, we can see that slope is that this slope can be calculated like that, delta T by DL by R. DL by R is basically length scale, DL by R, that is diffusion coefficient divided by the growth rate. So diffusion coefficient is there in front of the solid phase, and some boundary layer also exists, the solid reach boundary layer between the solid and liquid phase. So once the solid liquid interface is moving, if you follow the third figure, the solid phase is there and liquid phase, between that there is a solid reach boundary layer it forms. So and it is moving and the growth rate equal to R. In this case, the solid reach boundary layer can be calculated like that, DL by R. It depends on the diffusion coefficient divided by the growth rate, that actually increases the boundary layer thickness in this particular case. And then delta T by boundary layer thickness, it actually indicates the slope, and that slope is more with the actual slope equal to G. Actual slope G equal to here, the temperature gradient. So if you see the temperature gradient, this is the actual slope, and T and distance from the solid liquid interface, the actual slope G is less than delta T by dl by R, or G by R less than delta T by dl. So these actually conditions create the stability of the solid liquid planar solid liquid interface. And you can see that constitutional supercooling is there. If there is existence of constitutional supercooling, that actually creates some kind of the solute rich boundary layer. And here we can calculate the boundary layer thickness is basically depend. It's looking into the diffusion coefficient and the growth rate. That means what is the rate the solid liquid interface is actually moving. So based on that, we can calculate this boundary layer thickness, and all this calculation we can see. So breakdown of the planar interface is possible if G by R less than delta T by dl. So that means G by R value is the low as compared to the delta T by dl, then planar interface will break down and it will convert it to a cellular interface, and cellular to gradually the kind of the dendritic interface will gradually transform this way. But condition is that G by R, this depends on the G by R and delta T by dl. So it depends on the growth rate, temperature gradient, and delta T is the range between the solidus and liquidus temperature, and dl is the diffusion coefficient for this particular alloy system. That means diffusion coefficient means that the diffusion coefficient of the solute into the liquid for this particular alloy system. Now here you can look into this thing. The shaded area in the zone, the constitutional supercooling where liquid alone is actually unstable, and definitely in this particular zone, solid liquid coexist together. So thickness of the boundary layer can be calculated at the steady state equal to dl by R dimension. But to avoid there might not be any constitutional supercooling, it means that G by R should have very high value as compared to delta T by del L. So therefore, when to avoid the constitutional supercooling, it might not be the zone might not be there. In that case, the planar interface is the more stable at the steady state. So it means that planar interface should be stable, G by R greater than equal to delta T by dl. Or other way, the constitutional supercooling will be there, or planar interface will be unstable. In that case, G by R should be less than equal to delta T by dl. So these are the conditions. Now, planar interface, if the breakdown, it will try to break down to a cellular structure or a dendritic structure. So that solid cell or the dendritic can coexist within the intergranular or intercellular or interdendritic liquid. This dendrites can coexist with that. Now, if you see G by R, so that means higher G by R ratio, high value means either G can be very high or R can be low. In that case, that actually creates the stable planar solid liquid interface. So G by R ratio is very high. That creates the situation of the stable planar solid liquid interface. On the other side, if higher delta T and dl, that means this undercooling delta T and the dl, if the higher value of these things is actually, it means these are the delta T is very high or dl can be low, then in that cases it is very difficult to retain the planar solid liquid interface to be stable. So these are it means to say that G by R actually decides the stability condition of the planar solid liquid interface. Now here you can give more understanding on this thing, that solidification mode, which case is the solidification mode. Graphically we can understand that the planar cellular dendritic and aqueous dendritic, that condition is that if you look into this, the solid phase and this liquid phase and the interface, the equilibrium temperature is T, the slope is very high, and it doesn't create any kind of the shaded zone. That means there is no constitutional supercooling in this case. There is no constitutional supercooling. It means that it is create the condition of the planar solid liquid interface. Now cellular means much more this the shaded zone, that means this zone is there. In that case, it will create the cellular kind of the structure. Cellular structure is stable here. And further, if the constitutional supercooling zone is much more, then it creates the columnar dendritic structure at the solid liquid interface. If it is even much more, then it will create the aqueous dendritic structure. So the constitutional supercooling aqueous dendritic structure. So zone is, there is absence of the zone in planar to gradually, if is the increasing the constitutional supercooling planar to the aqueous dendritic. So planar is the minimum, or there is no constitutional supercooling, or the aqueous dendritic, there is a maximum amount of the constitutional supercooling. So these are the different zone at the solid liquid interface. They actually decide the different structure solidification mode: planar, cellular, columnar dendritic, and aqueous dendritic structure. So therefore, the zone where the dendritics and the liquid phase coexist is called the Musi zone. That we can see that liquid and the solid phase coexist, that the Musi zone. But at very high degree of constitutional supercooling, usually the Musi zones becomes more wider. So Musi zones area is much wide, and which actually promotes the aqueous dendritics to nucleate. So in this particular situation, so that means the Musi zone, that means the range between the solid and liquid temperature actually decide the range of this much more. And chances of the constitutional supercooling is much more. Musi zone is much higher. The zone is more wider, and that actually promote more aqueous kind of the aqueous dendritic kind of the structure. Here, other aspect also, effect of the cooling rate. That was the effect of the different solidification mode. Now, effect of the cooling rate. Here you can see the temperature gradient, the growth rate affects the solidification microstructure. So product of G and R. G is the temperature gradient and R is the growth rate. If you R into G is basically creates the dimension L by theta. So that means length scale divided by temperature. So that actually is known as is basically L by time. So it actually is the product of G into R is also known as the cooling rate. So therefore, it actually indicates the cooling rate. So length by time. So the ratio G by R determines the mode of the solidification. So here you can see the G by R, because in the previous slide we discussed about the G by R. So G by R is basically what kind of the mode, whether it is planar, cellular, columnar dendritic, or aqueous dendritic, that the mode of the solidification mode decided by the G by R ratio. But in that case, G into R actually decides the cooling rate. G into R governs the size of the solidification structure. Here you can see the G into R that governs the size of the solidification structure. It means that whether it is fine structure or it is a coarse structure, that we can see here. So greater into G by R is the finer the solidified cellular or dendritic structure. That means we cannot G into R decide the whether fine or coarse structure. You see the graphically we can represent the temperature gradient and the growth rate, and you can see these are the planar, cellular, columnar dendritic. These are different mode aqueous structure overlapping with this thing. This line indicates that the lower side low G by R. Here is the high values of the G by R. That actually decides the mode of the solidification. And if it is overlapping this line, so that alpha 1, the line corresponds to the alpha 1, the cooling rate, and alpha 2, where alpha 2 is the higher cooling rate than alpha 1. So alpha 2 is the fine structure, and that means the structure is the very fine, and where alpha 1 is the coarse structure. That we can see. So higher cooling rate is basically the finer structure, and lower cooling rate is basically coarse structure is usually from this case. Now, once we understand different mode of the solidification and the cooling rate effect on the structure, and now if we practically look into the one cast structure, it looks like that. Different types of the grain structure is the, if you see the equiaxed grain, crystal grows almost equally in all directions, commonly found adjacent to a cold metal. If you see, this is the typical solidified structure in case of the casting process. For example, this is the mold wall, and the liquid metal is there poured here. If you see the surrounding the mold wall, we can see the equiaxed kind of the grains we can form here, and then gradually columnar grains is usually formed. Columnar grains from this side, and columnar grain if you see, and that is try to meet at the center. So because nucleation exactly start just surrounding the mold wall, and gradually once it aqueous truck, then the temperature gradient becomes maximum towards the center. Then columnar grains usually forms this direction. So this is the typical structure, the solidified structure in case of the casting process. Now you can see the casting process also. Here you can see that how this liquid solid liquid metal the transformation occurs. If you see the liquid metal and solid liquid interface is there in between this thing, and solidified metal part is there, and sand mold there. And here you can see that transformation of the liquid into the solid during the casting process. If you see gradually it is solidifying, and it is moves towards the center. So at the center point is basically the last point where the solidification completes. So it entirely depends on the shape of the cast structure, shape of the mold wall. That actually decides that which part will be the solidified first and which part will be the solidified at the last moment. It depends on this structure. And also you observe there is a liquid metal, the solid liquid interface, we can easily observe the transition, the Musi zone also we can observe between the solidus and liquidus temperature. So it's a mixture of the solid and liquid phase. So this kind of the simulation, just looking into the temperature simulation, it is possible to see, or you can see the fraction, the solid fraction to the converting the liquid fraction. So this way you can represent the transformation from the liquid phase to solid phase in case of the casting process. Here other part is also there. The simulation, the microstructure evolution at the different cooling rate. This is the simulation, and we can observe the micro segregation of the solute elements between the dendritics. We can observe. Here you can see that columnar dendrite to the cellular grain morphology observed on increasing the cooling rate. If you see that columnar dendritic to the cellular grain structure, columnar to cellular transition is there. If there is a increasing in the cooling rate is increasing, and here we can see that means cooling rate alpha 1 to alpha 2, where alpha 2 is greater than alpha 1. But during this process, we can observe there is a micro segregation, but element segregation usually occurs. And this is completely simulation. You can see the segregation occurs. That means the composition changes at this particular point. Specifically, the interdendritic part, there is the element segregation usually occurs. If you see the cooling rate alpha equal to 0.1 Kelvin per second, alpha equal to 0.25 Kelvin per second, alpha equal to 1 Kelvin per second, alpha equal to 2.5 Kelvin per second. So these are the different cooling rate we observe, and then we see the columnar structure is also there, it forms. But during the formation of the columnar structure, it is basically columnar dendritic to try to form the cellular structure, but there might be having some formation of the some kind of the segregation at this thing. Segregation means basically there is a along this particular line there is a change, composition are not uniform. There is a composition actually changes during the solidification process. So segregation is one of the problem associated with the solidification process. But here you can see that one application of this thing, that mode of the solidification as well as the cooling rate, they actually decides the final microstructure, and that can be modified or that can be controlled, but that can be understandable just looking into the different solidification morphology associated with the particular array system. So that's all. Thank you very much for your kind attention. If you have any query. Maybe I think you can take this conversation in the different language. Okay, I'm not. It's very difficult to bring the terminology in terms of Hindi actually. For me, I think Mr. Shah think you have asked to explain in Hindi, but this conversation of this technical term in Hindi is, I think, difficult for me. But you can, anyway, you can convert. I think there is options are there, even class notes also. I think it is different languages. It has been changes, different language you can convert as per your convenience. That is also available. I think they have introduced, NPTEL has introduced to change in the different regional languages also. So I think you follow that particular the language, both text as well as the, I think, voice also. Okay, it seems there is no this thing, query and all these things. Maybe I can stop here then. Madam, I can stop here, I think. Please stop.